Okay, so work done by a force. Let's see. I am pushing this piano. This is me. Okay, I'm pushing this piano by a force F. And the piano decides to slide down because I'm not applying enough force. This piano is too heavy for me. So instead of moving upwards, the piano is falling down. Kiranya I'm also tertolak lah. So displacement is this way, but force is this way. So we have negative work done. So work done by force of gravity is negative. Work done by pushing force is negative. Kejap. Only upward, sorry. We are talking about downwards. Work done by force of gravity is positive. Why? Work done by pushing force is negative. The pushing force was done by me. It is in the opposite direction as displacement. So negative work done. Work done by force of gravity is positive. So let's see, this is our gravity of the piano. If I were to resolve this, I will have the effect, sorry, this is Wx and this guy is your Wy. Sorry, terbalik. Betul lah. Sekejap. If you were to resolve this, this is the angle. Okay, so this is Wy, this is Wx. So your Wx is in the same direction as your displacement. So Wx positive. Let's say going down is positive, and delta x is also positive, you get positive work done. This is the force by gravity. Okay, I said that whatever that is in the inclined direction is my x. This is just labeling. So the component for the weight in this direction is in the same direction as displacement. This gives me a positive work done. That is when my piano is sliding down. Okay, so now let's take a look what happens when the piano is sliding up. I am pushing the piano upwards, but now my displacement is this way. So it is in the same direction. So the work done by the pushing force is positive. Yay, we are doing something valuable now. And then the work by gravity is going this way. This is the force by gravity and the displacement is upward, so it is a negative. So you would ask me, Doctor, kenapa tak tengok Fnet je? Yes, eventually you will look at Fnet and the direction of Fnet in relation to displacement. But sometimes the question will ask you, what is the work done by the force of gravity? What is the work done by the pushing force? What is the work done by the reaction force? So those are the questions that can be asked. So you have to know all these separate forces and what their direction are to know what your work done is. Tapi eventually you will have to know what Fnet is to find out the total work done. Okay, let's take a look at an example if there is one. Okay, so work done by multiple forces. What are the forces? So this is a box. We have a reaction force going upwards. This is the pulling force. Typically, I label this as capital F. This diagram says it's a P, that's fine. We have friction opposing the motion. Displacement is going to the right. So this is my delta X. Now, I told you work done is only, there's value to work done only if it's parallel to the displacement. Our reaction force is not parallel to displacement, it is perpendicular. So Newton R and delta X is 90 degrees, right? So this gives me a 0 work done. Okay, because it's perpendicular. Remember the dot product is N cosine D. Cosine of 90 is 0. So the work done is 0. Okay, friction, the angle between friction and the displacement is 180. How do I know this? I extend it. So this is my X direction and this is my F direction. The angle between them is a half circle. So it's 180. 180, remember we decided that this was negative work because it's in the opposite direction. If you don't want to care about the angle, just look at the direction. If they are in the same direction, it's a positive. If it's in the opposite direction, it's a negative. So this guy is in the opposite direction. So this is, sorry, this is not 0. So this is going to be negative work done. Okay, pulling force. remember to resolve. So your P will have your PY over here, PX over here. Yes, it's positive work done. Good. And then our last one, MG. MG is perpendicular to displacement. So this guy is 0. So eventually total work done is W, work done with respect to the work done by the force of gravity, work done by the pulling force, work done by the reaction force, and work done by the friction force. And you already know which one is 0, just this guy. So this leaves us with the work done by the pulling force and the work done by the friction force will give us the work done, the total work done. Okay, so this is just the concept. Let's hope we have an example next. Okay, this is not it. Mana bagi example dia? Is there any questions for me? Okay, this is the example. Any question? Yep.
Then from the two components, we have the pulling force and the friction force. So we get F net from there.
Yes.
Between the two forces?
Yes, you can get F net and then times it with displacement. Boleh juga.
Thank you, Doctor.
Okay. Let's do this one as an example. No questions, Selain Bell? Okay. Hope everyone is alert. Okay, so this is D. Let's do this one. So a block of mass 25 kilograms, so the mass is 25 kilogram, is pushed 1.2 meters. So this is our delta X. This is our mass. Okay, so delta X is 1.2 meter. Along a frictionless horizontal table. So we don't have friction. No friction. Oh, I'm losing my voice. By a constant 36 Newton force. Okay, so F is 36 Newton directed below the horizontal. So let's try to draw this. It's very important to draw it. So this is your box. Below the horizontal. First, I label my horizontal and the 35 is below the horizontal. How would that look like? How would that look like? Anyone? Anyone wants to try? Should it be, okay, I'm going to give you options. Should it be the yellow guy? Should it be the pink guy? Should it be the green guy? Or should it be the purple guy? Which one? Which one?
Doctor, I think it's the pink guy.
The pink guy. Okay. Any other
Pink
answer?
and purple.
Pink and purple.
Purple, pink.
Purple and pink. Okay, jawapan dia purple and pink I told you there's always two sides to everything. Kalau dia tak specify from the left or from the right, so you have two options. It can be here or it can be here. Good. Okay, you are learning how to read the questions now. Okay, good. Okay, let's draw it balik. Okay, so this is our box. This is our horizontal. It's below the horizontal by 35 degrees. Remember, drawing this is as important as solving it because this is where you start. Okay, so determine the work done by the applied force. So now we have to do the free body diagram. Let's do this in yellow. So we have applied force. This is our applied force, F. The normal force exerted by the table. So we should have a table down here, but I forgot to put it. Okay, so if there's a surface, we have contact, then we have reaction force, R or N. You can label it either one. Normal force, and then we have the force of gravity. Let's do yellow as well. Have the force of gravity, which is W equals to mg, or just W is fine. And we don't have friction, we only have force. Okay, so now I would like to resolve my F to make my life easier as always. So if I were to extend this, okay, boleh extend, tak exact pun tak apa. If I were to extend my force, I would resolve my Fx this way and my Fy to be this way. Boleh extend, tak extend pun tak apa. If you don't want to extend, you want to keep it here. So it's going to be this way and going to be this way. Sama je. Okay. If you can do this correctly, you will have it correctly here as well. Vice versa. Okay, so it's asking you the applied force. So what is the component that is parallel to the displacement? We haven't labeled our displacement yet. Displacement is this way. Assuming it's to the right. What is the component that is parallel to displacement? Anyone? Work done by
Fx.
Fx. Okay, so the component that is parallel to the displacement is Fx. If we were to put this in value, it's going to be F cosine theta, right? And this guy would be F sine theta. If I were to use this terus, boleh. So it becomes delta X. If I want to say F is the dot product between, work done is a dot product between F and delta X. So this would give me F cosine theta delta X as well, same thing. Okay, boleh. So nak pakai parallel component terus boleh. You want to expand this equation into this guy pun boleh. It gives you the same thing. Okay, so don't get confused. So now my F is berapa? 36. Cosine is, what is the angle between my F and my displacement?
30.
30.
35.
35. Okay, so that's a 35 and displacement is 1.2 and the answer is, kejap, I don't know. Can someone punch their calculator for me?
35.39.
35.39. Thank you. So the units is, this guy is in Newton and this guy was in meters. So Newton meter. If your displacement is in centimeter, please convert it to meters because your SI unit is Newton meter or joules for work done. This is PBL number 4.1. Okay. It's 35.4. Okay. And then it's asking you, what is the normal force exerted by the table? The normal force is R and our displacement is this way. So it's a 90 degrees between those two things. So work done by reaction force is 0. Boleh juga nak kira. Kalau rajin nak kira. So reaction force, alah saya malas nak kira. Korang kira lah sendiri. Saya malas lah. Tapi boleh if you were to calculate this, you will still get 0. Okay? Because the angle is 90. So and then we have work done by gravity. And of course, this is also 0 because gravity is this way, displacement is this way. So 90 degrees, don't have to calculate, you already know it's going to be 0. And then the last one is net force on the block. Kena kira juga. So what is the net force on the block that is relevant to work done? So what is the net force on the block relevant to work done? So Alanda determine the work done by the net force. So net force that is relevant to get work done is only the force that is parallel. So do we have a parallel component to weight? No. Do we have a parallel component to R? No. We only have a parallel component for the F. And the only thing in the X direction, which is in the same direction as our displacement, is just F. So the net force, the total work done, W net. Kena betulkan soalan ni. Kan total. Sebenarnya total lah, tapi dalam soalan ni cakap net. Sama je. So net. So you will say this is F net dot product with displacement. Okay. So F So the forces in the x direction is only fx. So we have f cosine theta delta x. That's the only thing in the x direction. Remember, this dot product gives you a cosine, and the only cosine that we have that has value is f cosine from the pushing force. So this just becomes 35.4. Okay. Any questions? Is this confusing? Okay ke? Semua orang? Knock knock. Who's there? No one. Tak ada orang jawab saya pun. Are you guys okay?
Yeah, okay, doctor.
Okay. Apa? Okay, so that was the answer. This is the answer. Ni salah lukis Dia daripada atas. So it should be from here or here. It's below the horizontal. Okay, tengok balik soalan tadi. Bukan soalan. The slide. Okay, we'll discuss this one. Okay, work done by variable force. Just now we talked about a constant force. We pushed by 10 Newton, we pushed by 20 Newton, it wasn't changing. We had that force and it was constant. Now, physics would like to make our life harder by making the force variable. What does variable mean? Variable means that it keeps on changing. Macam biasalah fizik. What is going on? Why can't I use this? Baru kutuk fizik dah ke tak boleh pakai dah. Sekejap. Oh no. Oh no. What's wrong? Okay. Okay. Let's continue. Variable. Variable means keep changing, not constant.
Berubah-ubah.
Berubah-ubah. Apa korang ada yang benda variable ni? Manipulated variable. Variable tu apa? That's a different. Apa?
Pemboleh ubah, doktor.
Pemboleh ubah.
Pemboleh ubah dimanipulasi.
Wow. Okay. Saya percaya semua tu. Okay, because I didn't learn in BM. Okay, work done by variable force. It keeps on changing. The force acting on an object may not always be constant. For example, our elastic force of a spring is F equals to minus Kx, which means that if your X is 1, your force is different. If your X is 10, your force becomes different. This is your spring constant. It doesn't change. Kita dah belajar kan? Ke belum Tak ingat lah saya. Oh, belum. Sorry.
Doctor, is it F equals Kx or F equals to negative Kx?
Elastic force is negative Kx. Kenapa?
Sebab dulu in sekolah, we learned it as F equals Kx.
Okay. So, actually, there's
something new to learn.
Okay, so actually, this is your spring, right? Okay, sorry lah, spring ni buruk. So, elastic force is always opposing whatever that is doing. Contohnya, it's stretching. Okay, saya kena pakai warna lain. Ni just, macam nak cakap. This is, you don't have to know this much yet. This is for next semester, but I'm going to tell you anyways. So, if your spring is stretching this way, elastic force to the gale, it will always try to oppose this. This is F elastic force. So if my displacement is this way for my spring, it will oppose it. If I am compressing it, my elastic force will go this way. So it is always F equals to minus Kx. It's opposing the displacement. If displacement is going to the right, F is going to the left. If displacement is to the left, your F will go to the right because it wants to oppose this change. If you can imagine, when you try to stretch a spring, it's hard to stretch it, right? Because there's an opposing force. Wherever you try to stretch it, there's an opposing force that doesn't want you to stretch it. It wants to go the other way. And if you were to compress it, it's hard as well. You would think that when you stretch it, it wants to oppose it, and when you compress it, it becomes easier. No, when you want to compress it, it's still hard because there's an opposing force. The elastic force always tries to oppose you. So that's the elastic force. Tu baru elastic force Sabar. Yeah, F equals to Kx tu yang benda korang belajar.
Kalau elastic force, the work done is always negative.
The work done is always negative. Betul? Yep. Okay.
Thank you, Doctor.
Alright. So that is your elastic force. I'm going to label it as F E F. Boleh lah. So that is the that is the force by the spring. You are applying a different force. You are F applied. What is F applied? F applied is the opposite of FEF. Why? Third law. Newton's third law. Apa tu? What is it? Force is equal and opposite, right? You always have a reacting force that is equal and opposite. So force by the spring is FEF. The force that you are applying, whether you want to compress it or stretch it, is F applied, and that is always the opposite to FEF. Does that make sense? So maybe the one that you learned was F applied equals to KX. Boleh juga. It depends on where you are viewing the problem. Are you viewing from the angle of the person stretching it or compressing it? Or are you viewing it from the perspective of the spring? So there's two sides to it. Does that make sense?
Yes.
Okay. So that was the first one. Oh, panjang cerita. Okay, so illustrate force between charges. So this guy is F equals to KQQR. We won't touch much on this one because yang ni macam agak complicated sikit dia punya equation. Basically, this is charge 1 and then this is charge 2. Charges, different charges, and then this is the radius between them. And this is your force. Elastic force, this guy is a positive. If we were to consider the applied force by outsiders, it's a negative because it's opposite. But the electric force between the charges is F. But of course, macam mana kita nak kawal charges kan? So it's always a positive because electric forces is from the charges itself lah. An external force is not applied for this. Tak apa. We'll just focus on spring. This one is complicated. Okay, so in such cases, the total work done is given by work done FTX. So if I were to integrate F applied, which is the opposite of elastic force, I will get KX. So this guy represents the final displacement, and this guy is the initial displacement. So you will have to know if your displacement starts from 0, starts from 1, and then where does your final end? Does it end at 10? Does it end at 11? So I know the displacement is the final minus initial, right? But here for integration, you put in the values, okay? So let's say our xi is 1, our final displacement is 11, the total displacement or the change in displacement is 10. But you don't put in 10 there, put in 1 and 11. And kx with respect to 1 and 11 with respect to dx, if you have learned this before, I'm not sure, it becomes kx squared over 2. Do we have it here? Okay. So integrating this gives me kx squared over 2, and I need to plug in x1 and x2 into this equation. I don't know how to tell you maths. Not sure what the terms are, but this is your final equation. Okay. So this is when you have a variable force. Work done is the integration of force from displacement 1 to displacement 2. So this is your equation. Is it important for you to know this equation? Yes. Is it important for you to integrate this equation? Not really. I think you just need to know this equation. And if they were to say, what is f ax? Integrate ax with respect to x. Integrate ax with respect to a. So just know the basic concept of integration, you would be fine. Okay, so work done is this guy. If it's a variable force, work done is this guy. If it is a constant, sorry, it's a delta x. Okay, work done is this guy if the force is constant. Work done is this guy if the force is a variable. Okay, you can also put F here. Boleh. Okay, this is too much, too much. Okay, graphical representation of work done by a force that is variable. It's a variable force. For example, we have F equals to mg. The work done is tak, ni tak variable, sorry. This is a straight line. It's not variable. It's a constant. This guy is a variable. The F increases with X. The F is constant with H. The F changes with R. So this is a variable. Okay, again, this is a straight line, which means that my F is a constant value even though my H keeps on increasing. My F keeps on increasing when my X increases. My F keeps on decreasing when my R increases. So these two are variables and this guy is a constant. Okay, so what in the world do these graphs tell us? So the area under the curve is work done. Okay, so area under the curve. For example, what is the work done from H equals to 1 to H equals to 10? So let's say this is 1 and this is 10. So the work done is this box. So F is, let's say F is a 5. So what would that give me? Area under this curve is 5 times 9. Kan? So it's 45. This guy is a Newton, this guy is a meter. So you get 45 Newton meter. Area under the curve. So just kira box ni apalah. Kalau area under the curve the triangle, kira lah triangle. Okay? So it depends on the shape of the graph. So this guy you can make it into a triangle and a box. So add these two together, you get your work done. So now the question comes. Okay, so we already calculated the area under the curve, which is work done. Is our work done positive or negative? It depends on whether you are talking about F applied or F elastic force. So for this guy is F equals to minus kx, right? So this is the elastic force. So if this one, soalan dia akan tanya, what is the F applied contohnya? So you will label this as F applied even though this equation is given, but they are asking you what is a F applied to stretch a spring. So your work done will be positive. But if they were to ask you what is the work done for a elastic force? So this guy becomes negative. Walaupun area under the curve to positive, your final answer will be negative. Does that make sense? The area under the curve only
Yes,
gives you the
teacher.
magnitude. Okay, again area under curve kasih magnitude je. Gives you the magnitude of work force. Magnitude of work. But to determine if the work done is positive or negative, you have to look at the question. Whether it's elastic force, that's going to be a negative. Whether it's applied force, that's going to be a positive. Okay, you have to look at the question. Okay, area under the curve. Okay. Okay, so that's that. Okay, problem solving strategy. Read and understand the question. Visualize, sketch. I have to stress this. Always try to draw it. Ramai lagi yang malas ni. Selalu hantar saya gambar sekerat jalan. Tak boleh Identify all forces acting on the object. Sketch the free body diagram. Identify the displacement. If it's going to the right, if it's going to the left. And then resolve your forces. Find out if they are parallel or not. Okay? We already done this. You know this. State your answer. Do not forget units. Okay, we already done this problem. Okay, energy. You need energy to do work. Definition of energy is the capacity to do work. So kita memerlukan energy untuk buat work, kan? That was a bad explanation. Okay, you need energy to do work. When work is done, there is a change in energy. You decrease in energy. Contohnya, Nabi Hahla, dia buat kerja dapur. Kerja masak-masak. So after cooking, she feels tired. That means that after work done, there is a decrease in energy. Sebab dia penat kan? Okay, so tu Nabiha, dia rajin, dia nak masak-masak. Tu Haiman pula. Haiman apa? May-on eh? Is Haiman May-on?
Yes.
Oh, okay. Sorry, lupa. Okay, so Haiman, apa lah? Okay, dia buat kerja apa ni? Mendebang pokok. So, work is done on the tree. The force is applied by May-on on the tree. So, there's work done, positive work done. Energy is lost by May-on. He feels tired afterwards. Okay, so how do you gain back this energy? You eat. So that is positive work done on May-on. May-on eats. Positive work is done on May-on. So May-on has an increase in energy. Okay, basically buat kerja, hilanglah energy. Makan, dapatlah energy. So you can increase and decrease your energy. So, tu je lah nak cakap kat sini. Okay. Energy is a scalar quantity. The unit of energy is the same as work, which is joules or Newton meter. Sama So what are the different types of energy? Energy, we have kinetic, we have gravitational potential energy, we have elastic potential energy. These three are mechanical energy, which means it's a moving type of energy. Okay, it's moving type. Then we have electrical, we have chemical, and we also have nuclear. Okay. So we're going to focus on kinetic, gravity, and elastic for this course. Okay, so the energy of an object is associated to its motion. We know that. Kinetic energy is 1/2 mv squared. I'm sure you have seen this, whereby m is just mass and v is velocity. Okay, so Ke, kinetic energy is 1/2 mv squared. Okay, just a little recap for you there. Okay, so how did we derive this equation, 1/2 mv squared, from work done? Why does work done have the same unit, Newton meter, as kinetic energy? Because work done is equal to Fs, and we know that F is equal to ma, right? And we know that A that we are using here is the average velocity, is the average acceleration, which is given by, we can use this kinematic equation, v squared equals to u squared plus 2as. Remember, the kinematic equation is always using average acceleration. It's not instantaneous. So we can use this equation to plug it into our equation. Okay, so expanding this, mv squared over 2, this s cancels out, mv squared over 2, mu squared over 2. This gives me final kinetic energy minus initial kinetic energy. Kenapa final? Kenapa initial? This guy is a U, it's an initial. This guy is a V, which is our final. So this is final kinetic energy. This guy is initial kinetic energy. So this guy becomes change in kinetic energy. Wow. I know. Suddenly it becomes a change in kinetic energy. So again, kinetic energy, when it's just the equation, is 1/2 mv squared. When you have a change, there is something to be deducted lah. As usual, final minus initial. Remember when delta x, it was xf minus xi. So we also have that for kinetic energy, which is the change in kinetic energy, which is this equation. Sama. Okay, any questions so far for me? Is everyone okay? Am I going too fast? Do I need to repeat myself? Okay ke? Ngantuk lagi? Habis kelas apa?
Tak.
Okay, that's good. Okay, continuing. So work done on the object is K final minus K initial. This guy is our work energy theorem. Very important to remember. Maybe the question, the exam can ask you, what is the work energy theorem? So you have to know this equation. What is the work done? So you have to know there are two types of work done. W equals to F dot delta X, or W equals to this guy, F dx. Okay, these are the possible questions that will give you 1 mark. Definition of equation. Okay, I forgot to tell you. When they ask you what is the definition of work done, what is the definition of work energy theorem, you can give the equation, it's fine, but I wouldn't know if you know what W is, I wouldn't know if you know what F is, I wouldn't know if you know what delta X is. So you have to tell me where W is work done, F is force, and delta X is displacement. You have to macam ada disclaimer lah that you actually know this equation. If not, I would say, oh, dia ni tahu W je kot. Entah W tu apa? Apa W? Wheel ke? Bukan lah kan? Okay, weight. Yes, boleh lah. That's more scientific. I was going to say wheel. But yeah, I wouldn't know if you know what W is. So you have to tell me. Work done is W equals to dot product of F delta X. But where W is work done, F is force, delta X is displacement. You have to tell me that, okay? Ingat tahu, jangan lupa. Yep.
Doctor, we can only state this for questions which are for definition. For explanation, we cannot state the formula or the equation.
Boleh. You can always go above and beyond to answer your question. If there are, yep.
So to answer the definition, we use that first equation.
Use the first equation.
There's two equations.
And then explain.
Or what if we use the second equation? Is also okay.
If we use the second equation.
Yeah.
This one variable. Oh. Dia akan tanya kok what is the work done by a variable force. Kalau variable force pakai equation yang kedua. Ni variable Kalau dia tak cakap pakai yang ni. Kalau dia tak cakap pakai yang ni. Okay? Alright.
Thank you, Doctor.
You're welcome.
Doctor? The work energy theorem is only the formula in yellow box, right?
Yes. Tapi you have, it's better for you to put it like this. 1 over 2 mv squared minus 1 over 2 mu squared. Because again, I wouldn't know.
So finally, we must write the formula in yellow box, and the 1 over 2 mv square minus 1 over 2 mu square, and total is 1 over 2 mv square.
No, this is just K. The work energy theorem is delta KE. Lain it's different. It's the change in work done. So that's a good question. Kinetic energy and work done is different. Work done is the change in kinetic energy. Change in kinetic energy is given by K final minus K initial. This is your basic equation. This is when you have a change in kinetic energy. Okay? Is that clear?
Yes, thank you, Doctor.
Okay. Okay, if they were to ask you what is the work energy theorem, you can write this equation terus, boleh? You can write this as the first one, this one as the second one, third one, where M is mass, V is velocity, final velocity. You get the idea. You have to define all the apa nama dia ni? Parameters? No.
Units?
Not units.
Physical quantities.
What is it notation? Tak apalah, you get the idea lah. V is final velocity, U is initial velocity. Ada tak benda lain? Okay, tak ada. So you have to define what is M, what is V, what is U. Okay, so that was only kinetic energy, and change in kinetic energy is a different thing. So we're going to talk about gravitational potential energy and elastic potential energy. What time is it? Oh, lagi 3 minit. Okay lah. I think we're going to end class at this point. So next class, we're going to learn about change in gravitational potential energy, change in elastic potential energy, which is work done. Okay. Any questions for me before we end class?
Doctor,
Mm-hmm.
for the elastic force, F equals to negative K multiplied by X. The force applied is opposite to the force inside the spring of the molecule, right? Or it is the displacement? I'm not really understand about this.
Oh, okay. Let's talk about that. Okay, so this is me, and I have a spring. Okay, so I try to compress my spring, right? I try to compress my spring, and the spring compresses to become shorter now. Sekarang dia shorter because I compressed it. So displacement from this initial point, this is the displacement of the spring. This is delta X. The force that I'm applying, which is F applied, is 10 Newton. Okay, this is me. This is done by me. The spring opposes the same, minus 10 Newton. So F applied is by me, F elastic force is by the spring. The spring is opposing whatever that I'm trying to do. It will push me. If you try to compress the spring will try to push you. It's a lie. It will push you the other way. So the force comes from the spring, that is the elastic force. The other force which is applied is from you. It's not from the spring. Does that make sense?
Is that means that there are two forces when we apply the spring. The first force is we apply the spring in 10 newtons. The second force is the force of molecules in the spring that oppose the direction we push.
Yes, betul.
All right.
But the
Thank you,
displacement
Doctor.
is the same for both FA applied and both FEF. Okay. The displacement is the same
So,
because I'm pushing by this amount. The spring is also compressing by this amount. We both have displacement.
so which force we want to take for calculation?
Usually they will ask you F applied. Usually. So it's positive KX.
All right. Thank you,
Okay.
Doctor.
All right. Any other questions? So I'm going to stop recording. Stop recording. How do I do that?